Have you ever pondered over the significance of theorems in the vast universe of mathematics? In the intricate realm of math, theorems stand as towering pillars, each one a testament to the power of human logic and deduction. Theorems are not mere statements or mathematical conjectures. They are carefully crafted, rigorously proven propositions, each one a beacon of certainty in the often nebulous world of mathematical exploration. These statements, often of vital importance, are built upon a logical foundation of axioms and laws, forming the bedrock of mathematical understanding. You see, axioms and laws are the basic assumptions, the self-evident truths we accept in mathematics. Like the fundamental laws of physics, they are the starting point, the seed from which grows the mighty tree of mathematical knowledge. Theorems, then, are the branches of this tree, extending outwards, reaching for the stars of new understanding. The beauty of a theorem lies in its proof. A proof is a rigorous and logical argument that confirms the truth of a theorem. It's like an intricate puzzle, where each step is a vital piece contributing to the construction of the final conclusion. Every theorem carries with it a proof, a journey of logical steps and deductions that lead us from the known to the unknown, from the assumed to the proven. Theorems are the silent workhorses of mathematics, providing the structure and the scaffolding upon which we build our understanding. They play a crucial role in various disciplines, from algebra to geometry, from number theory to mathematical analysis, serving as the foundation upon which theories and practical applications are built. Consider the Pythagorean theorem, a timeless classic that establishes the relationship between the sides of a right-angled triangle. It's fundamental in Euclidean geometry and has been instrumental in countless practical applications, from architecture to navigation. In essence, theorems are the underlying harmony in mathematical structures. They encapsulate universal truths and provide profound insights into the relationships between mathematical concepts. They are the unsung heroes, the silent guides, leading us on our journey through the fascinating world of mathematics. But what makes theorems truly beautiful? Well, the beauty of theorems lies in their uncanny ability to encapsulate universal truths. They are like a mirror, reflecting the profound insights into the intricate relationships between mathematical concepts. Theorems are not just mathematical equations or propositions, they are the poetry of logic and reason. Consider a theorem as an intricate logical puzzle, a puzzle that teases the mind and challenges our understanding of the universe. Each theorem is a journey that begins with a simple assertion and ends with a conclusive proof. But this journey is not linear. It's a labyrinth of logical deductions and inductive reasoning, where each step, each statement, each proposition is an essential piece in constructing the final conclusion. Imagine you're in a dark room, filled with numerous doors. Each door represents a logical step, a proposition. As you open each door, you shed light on a new piece of the puzzle, revealing a path that leads you closer to the truth. The beauty of this journey is that there's only one correct path, one sequence of doors that will lead you to the final conclusion. The process of proving a theorem is like solving this puzzle. You start with a set of axioms, basic truths that we accept without proof, and use them to open the first door. As you progress, you find that each door leads to another. Each step builds upon the previous one, guiding you closer to the truth. And when you finally arrive at the conclusion, when you finally solve the puzzle, there's a sense of accomplishment, a feeling of triumph. You've navigated the labyrinth, you've unraveled the mystery, you've shed light on a universal truth. But the beauty of a theorem doesn't end there. The elegance of these proofs is not just in their ability to validate the assertions. They reveal the harmony in mathematical structures, the symmetry in numbers, the rhythm in equations. They show us the interconnectedness of all mathematical concepts, the unity in diversity. They make us appreciate the beauty of the universe, the beauty of logic and reason, the beauty of mathematics. The elegance of these proofs not only validates the assertions, but also reveals the harmony in mathematical structures. Wondering about the roles theorems play in various disciplines? Well, let's dive right in. Theorems are like the sturdy pillars that support the vast edifice of mathematics. They are the carefully crafted and rigorously proven propositions that form the backbone of mathematical reasoning. In the realm of algebra, for instance, theorems serve as the heartbeat, pumping life into the abstract world of symbols and equations. They provide the logical framework that helps us unravel the mysteries of numbers and their operations. Take the fundamental theorem of algebra. It guarantees that every polynomial equation of degree n has exactly n roots, or solutions. This theorem is a cornerstone in understanding algebraic structures and is used in a multitude of calculations every day. Moving on to geometry, theorems are the compass and the map, guiding us through the exploration of shapes, sizes, and properties of figures and spaces. The Pythagorean theorem is a shining example. It establishes the relationship between the sides of a right-angled triangle and is fundamental in Euclidean geometry. It's not just a theorem, it's a bridge connecting geometry with algebra, and it's used in countless ways, from construction to navigation, and even in computer graphics. In number theory, theorems are like keys, unlocking the secrets of the complex world of integers. Fermat's last theorem, for example, which remained unproven for over 3 centuries, explores the fundamental nature of numbers and their relationships. This theorem is a testament to the power and intrigue of mathematical exploration. Lastly, in mathematical analysis, theorems are the torchlight illuminating the path in the dense forest of limits, derivatives, and integrals. The mean value theorem, for instance, is a crucial tool in understanding how functions behave and change, playing a vital role in fields as diverse as physics and economics. So, you see, theorems are far more than just statements or propositions. They are the bedrock of mathematical theories and practical applications. They are the links that interconnect various branches of mathematics, enabling us to understand, explore, and create in this fascinating world of numbers and shapes. Theorems are the bedrock of mathematical theories and practical applications. Have you seen theorems in action? Let's consider a notable example. Take a moment and imagine a right-angled triangle. The magic of the Pythagorean theorem is in its ability to establish relationships between the sides of this triangle. Named after the ancient Greek mathematician Pythagoras, this theorem is a cornerstone of Euclidean geometry. But what does the Pythagorean theorem actually say? In its most basic form, it tells us that in a right-angled triangle, the square of the length of the hypotenuse, that's the longest side opposite the right angle, is equal to the sum of the squares of the lengths of the other 2 sides. It's often written as a squared plus b squared equals c squared. This theorem might seem simple, but its implications are far-reaching. It provides us with a tool to calculate distances, predict patterns, and even understand the shape of our universe. Let's consider a practical application. Say you're painting a wall and you need to reach a certain height. You have a ladder, but you need to know how far away from the wall to place it. You know the height you need to reach, and the length of your ladder. The Pythagorean theorem allows you to calculate the exact distance to place your ladder from the wall, ensuring you can safely reach the required height. Or think about GPS technology. It relies on the principles of the Pythagorean theorem to calculate distances between points on Earth. Without this theorem, we would be lost, quite literally. But the Pythagorean theorem doesn't stop at practical applications. It also helps us understand more abstract mathematical concepts. For instance, it's fundamental to the theory of trigonometry, which explores the relationships between angles and lengths in triangles. The Pythagorean theorem is a classic example of how theorems establish relationships and form the foundation of mathematical concepts. So, how do theorems impact our daily lives and the world around us? This might seem like a question for the mathematicians among us, but theorems actually touch every aspect of our lives, whether we realize it or not. Every time we use a GPS to navigate our way through city streets, we're relying on theorems. These mathematical statements, proven to be true, are at the heart of the algorithms that power the technology. Without theorems, we might still be using paper maps and compasses to find our way. Consider the field of physics. Theorems are at the core of our understanding of the universe. They help us predict the behavior of particles, describe the nature of light, and even understand the forces that shape the cosmos. Our knowledge of gravity, for instance, is based on theorems that were developed hundreds of years ago. In the realm of computer science, theorems are equally fundamental. They underpin the logic that drives our digital world. From the algorithms that dictate the operation of search engines to the encryption techniques that keep our data secure, theorems are everywhere. Without them, we wouldn't be able to enjoy the conveniences of modern technology. Even in economics, theorems play a critical role. They provide the logical framework that economists use to understand and predict market behavior. Theorems help us make sense of complex economic systems, guiding policies that impact everything from global trade to personal finance. And let's not forget about engineering. From constructing bridges to designing aircraft, theorems provide the mathematical assurance that these structures will stand strong. They help engineers calculate loads, understand material properties, and much more. As we can see, theorems are far more than abstract mathematical concepts. They are the silent workhorses that drive our understanding of the world. They shape our technologies, our economies, and even our understanding of the universe. Theorems, in essence, are the silent heroes, shaping our understanding of the world and the universe beyond.